concrete, it's not beautiful stuff, but sound-wise, this is a beautiful thing. When I was in choir, we sang in a church that had, God, like a 4.5 second reverb time, right? What they do to maximize reverb is if you make a perfectly rectangular space, the sound will get trapped between these walls and just die out. But if you just take one of the walls and just skew it slightly, in this case they skewed it like 4 inches. It was 4 inches wider near the altar than it was near the back of the church, right? The sound will sit there and do a crazy, boing, 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 the Pong game, right? Thing like that. And the reverb time is just amazing, right? Now the crazy thing about this is when you're singing, the tempo that you sing a song at, there's the harmony that's going on right now, right? That's written in the music and you can see that. But there's also a temporal harmony, a harmony of like I'm singing something and it's harmonizing with something I sang 3 beats ago. Yeah? That's tempo dependent. So when you get in a space and there's that kind of harmony going on, so these like medieval songs were sung in like cathedrals and stuff, and the harmony is pretty sparse, right? But when you sing the lines, you find that there's harmonies going on with stuff you've already sung with the reverb. And if you don't get the tempo right, it doesn't sound good. It's like, let's try this tempo. No, that's no good. Oh, that's nice. Then people come in and it changes the reverb time, right? It's like, oh, it's tough. It's tricky stuff, right? Okay. This is the St. Paul Cathedral. So I actually sang in here with a big group, and the poor conductor, she's sitting there with her tempo watch, just taking notes and writing things down, and eventually I think we actually got the wrong tempo, but that's all right. This is Notre Dame, and there's big signs there that says, don't sing in the church, or I would have sung in the church. Sicut erat in principio et nunc et semper. All right, there we have it. Well, because it's their church. I don't know. Be quiet. Other people, it's like there's not a service going on. You're not the singer. Other people are praying, and there's like, it's a religious space. So I don't know. And besides, what are they going to sing? Right? Okay, so any abrupt change, right? So more examples. Polynesian Navigators, it turns out that people couldn't figure out how they could navigate island to island out of sight of land. Like, you can see, 30 miles or something like that, right? These guys could navigate out of sight of islands, hundreds of miles with dugout canoes. How could they do that, right? It turns out that ocean waves reflect off islands, and people can learn to read those reflections off the islands. They can see them on the waves. Can you see them? No, you're not a Polynesian. You haven't spent all your life reading waves and ripples and stuff like that, right? And so there actually were anthropologists that learned, and it took a long time for them to learn what those reflections looked like. But eventually they could go, oh yeah, I see the reflection off that island, so I need to go more this way. Yeah? Isn't that wild? This is anthropologists do that, right? It's like it's either mysterious, aliens taught them how to do it, or it's a skill that's passed on from generation to generation that takes a long time to learn, right? How about long distance telephone calls? You call your sister in France, yeah? Hi. How? R. Have you ever heard that? A long distance call, right? It's like, what's going on here, right? Well, there's the US phone system. Here's the cable or the satellite. There's the French system, right? Right? The French, by the way, now have better internet and telephone service. Here's why. Because it used to be so crappy that they've had to replace it recently, right? Ours was good enough when we built it that we haven't gotten to the point where we have to replace it, right? But now you call, and every little change here can cause a reflection. You can get like, hi, right? Hi, right? Little reflections off of every time it changes like that, right? Okay? It just hasn't been done gracefully. Right, there's 2 ways to prevent reflection, right? You can just make it so the medium doesn't change. Force France, invade France, and make them use the same exact wires we do. Right? Okay. Or you can just make the change less abrupt. You can just make it more gradual. So for example, if you have a stereo, your stereo expects 8 ohms of impedance. It's more than just like the resistance of it. It's how it acts at frequency, right? If you buy a 4 ohm speaker, what happens is some of that energy from your stereo actually will reflect off the speaker. Yeah? Because it's the wrong impedance, right? And so what happens is that energy reflects back, your stereo gets hot. In fact, the part that gets the hottest on the stereo absorbs all that energy, the final stage of the amplification, right? Okay, and so the stereo will just get hot rather than like run your speaker well. And so when you turn it up to like 3/4 power, it's going to just burn out those transistors. This is sad, isn't that sad? Right? So what you can do is you can go to Radio Shack and get somebody to sell you an impedance transformer that just gradually goes from 8 ohms to 4 ohms, and that will reduce the reflections. Okay. How about sound? Right now I'm talking to you guys and the sound is coming up through my esophagus and it's coming out my mouth, and then it goes into this big wide room. Is some of that sound reflecting right here and going back in my head? All singers know this is true, yes? When you sing, you can feel the notes in different places in your head, can't you? Yes, you can. Okay, the sound reflects back and it makes your head shake. Okay, you're just used to it, but it's happening, right? How would I make more sound? Yes.
That's also how a lot of actors master new accents, is they can feel the vibrations just like that,
right? And it's how people who can't hear learn to speak. It's because you put your hand on the chest, right, and they can feel the vibration, and they do what makes their chest shake, and it's like, oh yeah, you know, you're making sound, even though you can't hear it, right? They can feel the vibrations, right? Okay, now, how would I get more sound to come out of my body? Wouldn't it be neat if there was some way that I could make it go from narrow little pipe to big wide room? What would that look like, I wonder? Like, would it be I don't know. Would it be, I don't know, something like, like this? Attention Kmart shoppers. This is my shtick. I always pick up traffic cones and say that. People are like, ooh, I want the cheap stuff, right? Okay, so let's do a little test here, okay? I'm just going to sing a little note for you. Is that any louder? I can't tell. Yeah, there you go, yeah. Partly it's also just directing the sound that way. Very little of it. It's probably getting maybe fainter for Natalie over there, right? Okay, which is just a shame, but you know, there we have it, right? All right. That's kind of cool, isn't it? Mm-hmm. This is, by the way, called an acoustic impedance transformer. A megaphone, yes? It goes from narrow to big. And they used to, by the way, when they recorded records, they had the recording equipment. There was no electronics. The first records were made without any electronics, and literally the force of the sound waves made a needle move up and down and etch lines in a sheet of plastic or something like that, right? Isn't this crazy? They're not plastic, but whatever they made those original records out of, right? Was it wax? Well, some of them were wax, but there were other ones that were like hard stuff. I don't know what it was, right? And so they would, if you were singing, you sang into one of those, and it concentrated the sound on one spot. And then if you see the old recording things like violins and stuff, they put things on them to make them louder. Imagine making a violin louder. And then they all sat on these benches and played into one of those big things. Yeah, it's just like, that's just crazy, right? Right? More examples, the wave device, bells on horns. So what's this on a horn? We've got a bugle up at the homestead, up at our cabin in Wisconsin. It's the original place where my Swedish settlers stayed, and the bugle can be taken apart. Apparently it's like a Boy Scout bugle, and you can like put it in your back pocket or something like that, right? And one of the fun things you can do is take the bell off the horn and hide it, and then if somebody tries to play it, it makes almost no sound at all without that bell, right? And it does crazy, like the sound energy is reflecting back and forth, and so it's just doing crazy stuff on your lips, right? It's like, ooh, tickly, right? Because the sound can't get out of the horn, right? So that's what these things are for, is to get the sound out of the horn, and get it from this enclosed space to out in the horn. And then the slide is just changing the length, right? Out in the hall, we change the length of that wave. That changed the frequency. That's what they're doing, right? That's one of the ways you change the frequency that you can do. All right. And then an anechoic room. An anechoic room is a room that is not echoey, correct? Yeah, there we go. And what they do is they just make the transition from air to, I think this is the right way to go. They make the transition from air to not air as gradual as possible. So there's all these little fins and baffles and things like that that go in there. And the idea is that the sound is going to get in there, it's going to reflect around, and it's not going to come back out. It's not going to reflect from there. Now, has anybody ever been inside an anechoic room?